Hello friends, this is Josh. Welcome to part 2 of this video on a pipe network and the flows of fluids within. So, in part 2 of this video, we are going to take this pipe network shown here, and we're going to solve for the flows through it. So our next constant that we're going to need is our rho, or our density. So our density of fluid, of water in this case, is going to be 1,000 kilograms per meter cubed. So that we're going to represent by that by just 1 times 10 to the third, so 1,000. So the next variable we need is going to be variable mu. Now mu, remember, is the variable that represents viscosity. So for this pipe network, our viscosity, we're going to take, our viscosity is going to be for water, which is 1 times 10 to the negative third Pascal seconds. And that viscosity will help, we'll use when we solve for our Reynolds number in this d-head function here. So after we input our mu, the last one we're going to need is going to be our internal roughness of the pipe. So if our internal roughness is going to be 0.001 as given in our given information. So running that, now that we have all of our given information, what we're going to do is we're going to move down to the bottom, and we're going to create an array for all of our pipes. So again, I'm going to put up our pipe network. So I'll let you guys see it. So in our diagram, we're going to have 4 nodes. We have node 0, node 1, and node 2. We're shown on the diagram. We're going to take the environment that node 1 and 2 are outputting into. We're going to take that as node 3. So in this network, we have a total of 5 pipes. So what we're going to do is we're going to create an array. We're going to call it pipes. And then we're going to create this array using numpy here. Call up an array. And this array is going to be, we're going to make it a 5-row, 4-column array. 1 row for each pipe. And our 4 columns are going to be the origin of the pipe, from node, the destination of the pipe, the to node, the length of the pipe, and the k-value of the pipe. So what we're going to do is we're actually going to put a little comment here, so I remember which goes where. So we have our from node, and we're going to put that as the first column. Remember, since we are working in essentially with Python as our base code, Python always starts its indexing at 0. So even though it's our first column, we're going to call it 0. Then the next one is going to be our to node, and we're going to put that at 1. we have our length at 2 and our k value at 3. So back up to this array. We are going to go to first pipe. So the first pipe starts at node 0, goes to node 1, has a length of 20 meters, and a k value of 1. Okay? So, what we're going to do, and then we're going to do the same for the next 4 pipes. So, the second pipe is going to go from node 0 to node 2. It has a length of 30 meters and a k value of 1. Our third pipe is going to go from node 1 to node 2, has a length of 5 meters and a k value of 1. Our fourth pipe is going to go from node 1 into the environment. So again, that's going to be node 1 to 3 because we're defining the environment as our node 3. Has a length of 0.1 and a k value. Its k value is unknown. However, for this problem, we are going to guess that its k value is around 6. And the reason why we guess is because we're solving for the flow within this network. And in order to solve the flow within the network, we need to have some starting points. So we're going to just guess that it's 6. And likewise, we're going to guess that the height of node 0, is at 15 meters. And we're going to carry these values in throughout the rest of this network. So, the final pipe in this network goes from node 2 to node 3, has the length of 0.1 and a k value of 1.0. So, clicking this off, we have all of our commas. It looks all good to go. Okay, so after we have our array of pipes, what we're then going to do is we're going to add in the rest of our given information. So what we're going to do is we're going to create an array that houses all the heights of the nodes. So we're going to call this Z, because Z is our usual value for vertical displacement. So we're going to create an array, same as above. And the first node is going to be at 15.0, because that's what we're going to get. That's what we're guessing for this problem, as stated before. Then the rest of the nodes are all at a height of 0. So we'll just put in 0, 0, and 0. Okay. And then next we're going to specify the pressures that our external nodes are at. So the way we're going to do this is we are going to, first we have to define which of our nodes are external nodes. So the way we're going to do that is we make a variable called external pressure indices, so the index of our external nodes, and we're going to call this node 0 and node 3. And what this is going to do is this is going to create an array of a 0 and a 3. So when we're going to use it later, it's going to signify that our node 0 and our node 3 are going to be our external nodes. Then we can compare that to our internal nodes of 1 and 2 to get our full system. So now that we have our indexes, we're then gonna put in our pressures for our external nodes. So our external pressures is going to equal another array. And we're gonna again reference our given information. So the pressure at node 0 is at 0, and our pressure at node 3, which is the environment, is also at 0. So we create this array here of zeros, and that'll serve as our given information. So now that we've specified our heights and our pressures at the external ones, what we're going to do now is we are going to calculate for, or we're going to input our diameter of the pipes and our internal roughness of the pipes. So the diameter of all of our pipes, they vary as we go. So we're going to have to create another array. So pipe diameter is going to equal numpy dot array. And so our first pipe, pipe 01, has a diameter of 0.1. So 0.1. Our second pipe from 0 to 2 has a diameter of 0.05. Our third has a diameter of 0.01. And our fourth and fifth also have a diameter of 0.01. So these are the diameter of our 5 pipes. Now what we're going to do is our internal roughness, ED, of all of our pipes all have the same value. So what we're going to do is we're actually going to use a little shortcut to create an array called a full function. And what that's going to do is it's going to take a number, and it's going to take a number and a value and create an array of the size given by the number filled with the value. So first thing we got to do before we can use that is you got to figure out the number of pipes. Sure, I could hard code it because we have 5 pipes, but I'm going to use another function called shape. What it's going to do is it's going to take this array here and find the shape of it. So let's see if we can get. So what this is going to do is it's going to count how many rows we have in column 0. It's going to see we have 5. And it'll output that we have 5 total pipes. So let's just check that. So n pipes. And we're going to Alt-Enter to run it. And there we go. So 5 pipes. So that looks good. So now we're going to do is we're going to use this number of pipes that we just calculated. And create an array for our roughness. So we're going to use the numpy.full function. And we're going to use our n pipes. And then we're going to throw in our given information 0.001. So 0.001. So we have something that can calculate the number of pipes. So we probably should make up something similar to calculate the number of nodes we also have. So the way we're going to do that is we're going to use we're going to kind of shortcut it. Because our network starts at 0 and counts up sequentially, all we have to do to figure out the number of nodes we have is to find the highest numbered node and add 1. So the way we're going to do that is we're going to use the numpy.max function, which will find the highest number, and we're going to run it through our pipes. And tell it to look, we're going to tell it to look in column 1 and column 2 and find the highest number it can find. So this colon here, what this colon does is it grabs all the rows with these columns. So 0 and column 0 and column 1. And then what we're going to do is we're going to add 1 to it. So we're going to double check to see if this one works. So number of nodes. Okay, so we got the right answer. We got 4, which is how many we know from the problem. However, a problem we have here is that we want this as an integer because it can be, and because it'll make it easier when we're doing arrays later. So what we have to do is we have to convert this, change this into an integer. And the way we do that is we use the asType function, numpy.int32. So when we check this again, we get this as the integer 4, which is how we're going to want it for later. So now that we have basically almost all of our given information, what we're going to do is we're going to take our from node values, our to node values, our length values, and our k values from this array so we can use them. So we're going to call this variable from node and make this, and we're going to pull every row in the first column. So the way we do that, we use the colon, like I said before, and we tell it to grab column 0. Okay? Then we're going to do the same with the to node. Grab every row of column 1. Then for our lengths, we're going to grab every row of column 2. And our k value is going to be every row of column 3. So that should get all the information out of this array we made. And so we can use it later. Because what we have here, I'll demonstrate. So pulling from node, oh, excuse me, forgot to run it. So pulling from node, we have this array 0, 0, 1, 1, 2. And you can see 0, 0, 1, 1, 2. So this is exactly what we want. We want this in an array. So if we ever call it back, we can use just a simple index to just pick the value we want for the pipe we want and use it from there. So that'll work for us. So now that we have all of this information, next thing we're going to pull out is all of our nodes that are within the are completely within the system. So again, we could hard code it the way we did with our external ones up here. We could do that. But what we're going to do is we're going to do something called a set subtraction. And we're going to create a list of all of our nodes and subtract our external nodes from that list of full nodes. So what that's going to look like is internal indices. It's going to be equal to the list set numpy dot arrange and nodes. So what this arrange function does is it returns evenly spaced values within a given interval. So for us, this is going to give us a set starting at 0 of all integers up to n nodes. So we saw n nodes is 4, as we saw down here. So this is going to give us a list, or a set, of 0, 1, 2, 3, and 4. Or, excuse me. It's going to give us a set of 0, 1, 2, and 3. Sorry about that. So what we're going to do is first thing we're going to do is we're going to then subtract this. Subtract this set that we just created by another set. A set defined by the external p indices that we got from above. So we're going to run that, and then we're going to test this. So just as we predicted, we have 1 and 2, which is exactly what I want, because looking at this picture, we know that 0 opens to the environment and 3 opens to the environment. But 1 and 2 are completely contained in that they have pipes going to and from each node. So this works. And then now that we have a list of internal indices, or an array of internal indices, excuse me, we can find the number of internal indices by just doing the length of that list. And that'll simply give us the amount of objects within that list. So it'll give us 2 objects. So now that we have all of this information, what we're going to do is we're going to calculate or set up an arrays to use for flows and net flow. So our flows function, or our flows array, we're going to create an array full of zeros equal to the number of pipes. So what that looks like, we can get rid of these now that they've served their use. What that's going to look like is it's an array of 5 items, 5 pipes, 1, 2, 3, 4, 5, of all zeros. And what we can do is we can then build up this list, build up this array by adding in values to it. So, likewise, we're going to use netQ, so net flow we're going to do the same by making another array of zeros, except this time we're going to use the number of nodes. And that'll do the same as this one, except our array for this one is only going to have 4 items instead of 5. So, now that we have flows and net flow, we're also going to want pressure, because pressure is going to be important for us. So, just as before, we're going to create an array of zeros. And these pressures are localized at each node. So we have node 0 as a pressure, node 1 as a pressure, node 2 as a pressure, and node 3 as a pressure. So we're just going to create an array of all the pressures of all these nodes and set them equal to 0 for now. And now what we're going to do is we're going to add in our external pressures. So as I said before, node 0 has a pressure of 0, node 3 has a pressure of 0. So, which I defined up here. Sorry, defined it here. So this will put in our external pressures into our created array here. So running this, we can then check our P array, and we get an array of zeros, which makes sense because our external pressures are also 0. So now what we're going to do is we're going to create a guess, just like we did up here, where we had to guess our friction factor. We're going to guess the pressure within these 2 nodes to try to get somewhere, or as a starting point. So the way we're going to guess these pressures, we're not just going to come up with a number out of thin air. What we're going to do is we're going to calculate the average of our external head at 0 and 3. So the heads at 0 and 3 and average them. And we're going to use that average to create a guess of our pressures within. So we're going to call this average external head, numpy mean, so numpy average, of our external pressures divided by our rho divided by our G plus Z, so plus our heights from this array using our external P indices. So briefly, what this function does is it uses our head function that we came up with earlier, pressure divided by rho divided by gravity plus height, and basically averages our pressures and our heights. So, running that, running this code again, we can run this, and we see our average is 7.5. And that will work for our purposes. So, what we're going to do is we're going to then use that 7.5 we're going to use that 7.5 to create an internal head guess. So we're going to do MP full. And again, we're going to create an array of the given shape. So this array here, internal indices, has 2, or this number has 2. So we're going to create an array of 2. And we're going to put our average external head in that place. And then we're going to do our internal pressure guess equal to our internal head guess minus the heights of our internal nodes. And then this little function here is all going to be multiplied by rho and our gravitational constant. So, run this, make sure that we have no errors. It all looks good. So, this is going to be our initial pressure guess. It's going to be our initial pressure guess for our internal pressures of the system, which is going to be at node 1 and node 2. So, that was a long piece of code, but we got to the end. And now what we're going to do is we're going to take a peek at what is our internal head guess. And 7.5, about what we expected. And our internal P guess is going to be equal to these pressures. These pressures are what we're guessing are roughly what's going to be in 1 and 2. It's not going to be completely correct, but it's a good starting point for our future calculations. Just like you saw how we had to guess on that other function. So, what we're going to do is we're going to create another function. We're going to call it q to 0 and do something very similar to what we did in our other function that we called f to 0. In f to 0, what we did is we iterated flow to find a friction factor that was correct, so that our drop in head was equal to our delta head. So our q to 0 is going to need the variable internal pressure, which we will get there in a minute. So what we're going to do is we're going to take this internal P and put that in as our internal values in this array up here. So we got P internal indices is going to be equal to our internal P, which we get from our input of this function. Then we have a brief function to calculate heads, which is just P over rho over G plus Z. So what this will do is this will calculate the head at each internal node and external too. Now, what we're going to do is we're going to iterate. So for I in the range number of pipes, what this will do is this will go through the number of pipes. So this pipe, this pipe, this pipe, this pipe, and this pipe, and calculate a delta head. So delta head is going to be equal to the heads, so this function up here, of our 2 node minus our heads from node of I. So briefly what this will do, this is to calculate our delta head. It's just head from our 2 node minus head from our from node. So using this function here, we're going to take our internal pressures and our external pressures, which are all in this P array, and we're going to run it through this function and subtract them from another. So that'll give us our heads, and then to find the flows of each pipe, we're going to call up our flows function that we created in part 1 of this video, so this flow function. Oh. So we're going to call up this flow function. And if you remember, our flow function required, this nice handy tooltip will tell us, it required a delta head variable, which we just calculated a minute ago. So we got delta head. Then we need our length, which we get from our array lengths here. So we got length of I. Then we need our k value, just k of I. Then we need we're going to need our diameter, which we call pipe D. And then our final argument for this is going to be our internal roughness, which we likewise created a array for here. Now what this will do, this takes our I, which iterates over time, and takes each pipe and creates a delta head, okay? So we're going to use this in a minute. And what we're going to do is we're going to zero out our net Q array. We had it set to zeros, but we're just going to zero it out by filling it with the value 0.0. That's just in case we want to run this again and again with different values, and so the numbers don't climb on top of each other. Then what we're going to do is we're going to do numpy add at netQ And what this will do, this will add our flows that we calculate here to all the two nodes. So 0, 1, 2, 0, 1, and 2 that we calculate for each pipe. And we're going to do the same thing, but with the from nodes. So net Q from node flows. Now, because we defined it in this thing that our to node was positive and our from node was negative with this delta head, we're going to make this flow negative. So we're subtracting the from node flows and adding the to node flows. And the goal is that our net Q for node 1 and node 2 can equal 0. Because if we can get that equal to 0, then we'll have our flow rates through the pipe, and that will be correct. So, now that we have all that, we can return our net Q for our internal indices. So that will give us our net Q. So after running this function, we'll get our net flow rate through our internal nodes of 1 and 2. And a quick disclaimer, if our net Q is positive, then the flow direction that we assumed in the picture is correct. But if it's negative, that means it's actually flowing in the wrong direction that we assumed. So, for example, if our net Q from 1 to 2 is a negative number, then that means it's actually flowing this way, and that we just picked the wrong one. So, what we're going to do is we're going to run this. Okay, no syntax errors, so we're good. Now what we're going to do is we're going to solve this function and zero it out. Because our goal is to get our internal indices net Q equal to 0, right? So we're going to just do answer. So our answer of this is going to be, so what we're going to do is we're actually going to have to import a new function all the way up here called root. And this root function, let's run this. Let's run them all. This root function finds the root of this vector function. So we're going to, our first argument is a function. So we're going to pull in this function here, Q to 0. And then what we're going to do is we're going to throw in our internal p-guess as our starting point. So if you remember, we calculated our internal p-guess by averaging our external heads and converting that average into pressure for each of our internal nodes. So internal p-guess will give us a starting point. And if we run this, we get an error. So let's take a look at this error. We have an error in this line, of course, and the error comes all the way back up to here, and it says our delta head equals heads to node I, heads from node I. Now, our error is an index error, which states that whatever we're using to index doesn't work. So this index here and this one come from this line here, which counts up 1 by 1, and we know that that's an integer. So that means the problem has to lie with our to node and our from node. So we want these to nodes and from nodes as integers. So going here, what we're going to do is we're going to run to node just to take a look at what our array looks like. So you can see here, this decimal tells us that this is not an integer. Instead, these numbers here are, they're probably doubles. So what we're going to do is we're going to have to go up here and convert all of them to integers. So the way we do that, just like we did with the number of nodes here, we're going to do as type np.int32. And we're going to do the same for this one, as type np.int32. So hopefully, if we hit here, run all, hopefully, okay, we have another error. We have pipe ed is not defined. So, okay, here's the problem. We have a typo. So I misspelled pipe ed. And so when the function tried to call it here, it couldn't find anything. So rerunning all these again, we have another error. Okay, so with this one, we created this variable here, abs delta head. But when we referenced it here, where'd it go? When we referenced it here, we accidentally added an extra underscore. So the reason why we're coming up with all these errors is because we're actually feeding numbers through these functions. And so any errors that are the result of these functions that aren't like clearly syntax errors pop up now. So running this through, we run this and it doesn't seem to have any problems. So what we're going to do is we're going to print out our errors. So the first thing we're going to do is we're going to check our answer. And we check it, and we get this. So we don't really know what these mean. But what we're going to do is we see that it converged, which is good for us. And we can see that our internal nodes are, well, we'll find out what these mean in a second. So what we're going to do is we're going to print out our answers into a format that is a lot easier to read. So for I in range n nodes, oops, forgot the colon, we're going to print f net q space curly bracket 1 then we're going to do another curly bracket net q I 9.5 f. So all these things we're doing are just formatting so that we can read it. So for example, the 9 means that we're going to want 9 spaces in total, and the 5 means we're going to round to the 5th decimal point. So now that we have our net q, what we're going to do is we're going to throw little spaces and show off our pressures. So P, we're going to do P of I, colon, 9.0 f. So we want to round the pressures to the nearest whole number, because the pressures are in pascals, which means they're going to be a bit larger. Probably in the hundreds of thousands, because the pressure of atmospheric pressure is already at 100,000 pascals. So we know that the number is going to be pretty big. So we have this. Then we're going to do is we're going to print just an empty line to space out our two statements. So we're going to print, and we're going to create a print statement very similar. And what this print statement here is going to do is up here showed our net flow and our net flow at each node and the pressure at each node. But this one, we're going to show off the flow in each pipe. So let's indent these. So our flow in our pipes is going to be, it's going to look very similar. We got our from node, I, to node, curly bracket, to node, I, and then we're going to pull in our flows. At I, and do 9 digits, 5 decimal places. Close the curly brackets. And we're going to specify the units. So we have meters cubed per second. And fingers crossed, we get this answer. So looking at this answer, we have our net Q at node 1 is negative 2 meters cubed per second, and net Q at this guy is 2 meters per second. And our flows at 2 and 3, or at 1 and 2, are equal at 0, same pressure and everything. So looking at this picture, it's kind of unrealistic that we're going to have the same pressure at both, considering we get to them at very different ways and this one actually feeds the other. So let's just double check to make sure we haven't made any errors with our calculations. So going through our code, we're going to double check that we have that our given information is correct. So we have 9.81 as G, that works. Pi as pi, that works. Our rho is 1 times 10 to the power of 3, which is the density of water in kilograms per meter cubed. We have mu, which is the viscosity of water, which is 1 times 10 to the negative 3 pascals seconds. And we have ED, which is our internal roughness of the pipe at 0.001. So all that looks good. Now we're going to check this Churchill function. 2.457 times MP log. So I actually pulled this. We pulled this function from online as one of our chemical engineering functions to calculate frictional factor. So looking at this, we have so that looks correct. 2 times 8 over RE, the power of 12 plus 1 divided by A plus B, power of 1.51. Okay, instead of doing that, we're going to take a look at this. So we guessed earlier that our internal P gas was this. And looking at this answer, we see that it didn't change. So that means we have a problem turning our internal P gas and finding zeros from that, like changing it. So looking, first time we find the internal P guess is right here. So looking at this, we have our average external head, average external P divided by rho divided by G plus Z of that. Internal head guess is just internal indices, internal head. That just makes it into an array. And then our internal pressure guess is head guess minus our internal indices times rho times G. Excuse me. So that looks okay. So let's go down to the next function we have. So our Q to 0 function uses our internal pressure as our input. So looking at P internal indices equals internal P. Great, that's our input. Heads equals P divided by rho divided by G plus Z. For I in range and pipes, we have our delta head equals the heads from 2 minus heads from the from, which makes sense because that's just a change in head. And our flows is using our flow function that we made earlier, delta head lengths K, pipe D, pipe ED. Okay, that looks, I don't see any problems here. So now net Q fill, 0, 0. 2 flows from negative flows. So we return net Q internal indices. That looks okay so far. So you have Q to 0, internal P guess. And for some reason, that spat out that we were right on top, which still doesn't make sense. So now we're going to take a look at our flow function. So going up to our flow function, we have our delta head, LKDED. So you have AB absolute value delta head equals numpy absolute value delta head. Okay, that works. If that's okay, so let's just quickly change this. Let's just change a few values, see if that makes any difference. So we got pi times d squared over 4 times the square root of delta head D head is this function. We have QLK DED minus absolute delta head. Result is going to equal our Newton function, F to 0, so this function, times Q guess, which is up here. And we're going to return our delta head Let's take the result outside the delta head and see if that makes a difference. So we're going to run it all. And now as you can see, that really changed our answer. So looking at this answer, we got that our internal pressures are different, which is good because we don't want them to be the same. They probably won't be the same. And our net Q in and net Q out are equal, which is exactly what we want. So after a little bit of debugging, we got an answer, and this answer makes sense. Because if we look at this, so we just guessed on the height of node 0 and the K value of pipe 1, 3. And we're trying to solve for an exit flow rate of 0.5 liters per second. And from node 1,3, which we wanted as 0.5 meters per second, or 5 times 10 to the negative fourth meters cubed per second, you can see here we have 5 times 10 to the negative fourth meters cubed per second. So node 1 to 3 is where we want. However, node 2 to 3 is a little bit off, because we wanted about half of this. Instead, we got 12.1 times 10 to the fourth, negative fourth meters per second. So our node 2 to 3 is still off, but I think that comes from the fact that we just guessed. Close, but not quite exactly correct. So this is just a brief, well, not quite brief. Sorry about the length. I'm a little slow typer. But this was a quick video on how to use Google Colab and Python to model a pipe network in order to solve net flows at each node and flows through each pipe, given some initial information. So thank you all for joining me, and I will see you when I see you. Thank you.